Welcome to the deep dive. Today, we're tackling a really critical topic. We're taking all that dense source material on secure software design and turning it into a focused, high-value study guide for you.
That's right. Our mission is very specific today. We're going to create a reliable map through the core concepts. We'll synthesize the Security Development Lifecycle, or SDL, break down the key frameworks, and really zoom in on those critical vulnerabilities and how to stop them.
And we're structuring this whole deep dive around the way you'll need to know it, focusing on those exam weights, definition, technical implementation, and process.
Exactly. So let's just jump right in. The most foundational concept, the one that everything else is built on, is the SDL itself.
Okay, so everyone knows the SDLC, the software development lifecycle, that's the engine. The SDL, the security development lifecycle, that's like the high-performance security upgrade for that engine.
That's a great way to put it. It's a systematic overlay. It's about making sure security isn't just an afterthought, a patch you slap on right before you go live. It has to be baked in from the very beginning.
And that idea of starting from the beginning leads directly to this core imperative I see everywhere in the material. Shift left.
Shift left. It's not just corporate jargon. It is an absolute economic and logistical mandate. It means pushing vulnerability identification and remediation as far left on the timeline as possible.
All the way back to the initial design and planning phase.
All the way back, before a single line of code is written.
I really appreciate that the sources frame this less as a philosophical choice and more as just a cold, hard business decision. The cost differences they cite they're pretty staggering.
They're exponential. That's the key. Because when you fix a security flaw in the requirements phase, what are you really fixing? A line on a diagram, maybe a document?
Right. It's cheap.
It's basically free. But when you find that exact same flaw after the product is deployed in the field, now you're talking about fixing complex, interconnected code. You're paying for emergency penetration tests. You're activating incident response team.
And dealing with all the fallout, the potential fines, the damage to your reputation.
Absolutely. The sources put a very clear number on it. The data shows that fixing a security flaw in the wild can cost anywhere from 50 to 200 times more than fixing it back in the requirements phase.
Up to 100 times, according to some of the data from Fortify. That's an incredible number.
It is. And that's why we say security is a business decision.
Yeah.
Missing an encryption requirement in phase A1 means you might have to re-architect everything in phase A5. That's a massive cost.
So if the SDL is the process, what are the fundamental goals? What are we trying to protect? This brings us to the classic CIA triad.
Right. The three most important non-negotiable goals for any secure software. Confidentiality, integrity, and availability. Every single security control we're going to talk about serves one or more of these three pillars.
Okay, let's break them down, starting with the one everyone thinks of first, confidentiality.
Confidentiality is all about keeping secrets. It's protecting data from unauthorized access or disclosure. We're talking PII, financial data, session tokens, anything that shouldn't be seen by the wrong people.
And the main tools in the software toolbox for that are access controls and encryption.
Exactly. Access controls to make sure only the right people can even ask for the data, and encryption to protect it both in transit over the network and at rest on a disk or in a database.
Okay, next up is integrity. This one can be a little more subtle than confidentiality.
It is. Integrity isn't about hiding data. It's about ensuring that the data hasn't been changed, either maliciously or accidentally. You need to know that the file you downloaded is the one the author created, or that the bank transaction wasn't altered somewhere along the way.
And we enforce that with things like hashing and checksums, right?
And that's the primary mechanism. You calculate a hash of the original data. When you receive it, you calculate the hash again. If they don't match, you know the integrity has been violated.
And finally, availability. This one seems like it can sometimes be in conflict with the other two.
It absolutely can be. Availability is simply about making sure that valid, legitimate users can access the system when they need to. It's your defense against things like denial of service attacks.
So the tension is that if you make security too tight, with too many layers of authentication, for instance,
you might hurt availability. The system becomes so hard to use that it's effectively unavailable. A great security architect knows how to find the right balance between all three for their specific application.
All right, that's a perfect foundation. Now let's move into the essential mindset and the frameworks that guide all of this. For anyone studying this is a big section, weighted heavily under definition and classification.
And we have to start with the foundational design principles. many of which go back to the work of Salzer and Schroeder. The absolute most important one, and probably the one that gets violated the most.
Let me guess. Least privilege.
The principle of least privilege, or POLOP. The idea is simple, but execution is hard. Every single user, every process, every microservice should only have the bare minimum permissions required to do its specific job. Nothing more.
It's so tempting to just grant admin rights to a service so you don't have to debug permissions later. Why is that convenience so dangerous in the real world?
Because it dramatically increases your blast radius.
The blast radius. I like that term.
It's the total potential damage from a single compromise. If an attacker breaches a component that's following POLOP, they're stuck in a very small box with very few permissions. If they breach a component you gave admin rights to just in case, they now own the whole system.
Can you give us a concrete example?
Sure. Imagine a microservice that just generates a daily sales report. All it needs is read-only access to one table in the sales database. If you give it full right and delete access to the entire database, you've violated POLOP. The second an attacker pops that one little service, they can now wipe or corrupt your most critical data.
That makes it crystal clear.
Okay.
Okay, the next principle seems to accept that failure is inevitable. Defense in depth.
Defense in depth is basically the security architect's version of don't put all your eggs in one basket. It's the understanding that no single security control is perfect. Your firewall will eventually have a flaw. Your authentication might get bypassed.
So you layer them.
You layer them, you have multiple independent controls. So you might have a web application firewall at the edge, then input validation in your code, then strict access controls on the database, and finally encryption on the data itself.
So if one layer fails,
the next one catches the attack.
Yeah.
A breach of the perimeter doesn't automatically mean a catastrophic failure of the whole system. It's like a medieval castle. You have a moat, a drawbridge, high walls, and then guards inside.
let's talk about what happens when things fail. The principles of fail securely and fail-safe defaults.
This is all about resilience. The core idea is that if your system crashes or hits an unexpected error, it must always default to the most secure state possible.
Which is almost always a state of denial.
Always. By default, access is denied unless explicitly granted. So imagine your central authentication service goes down. A system that fails open might just start letting everyone in. That's a disaster.
A system that fails securely would do what?
It would deny all access attempts. It might hurt availability for a little while, but it completely prevents unauthorized access during the failure. The system goes into lockdown, maybe only allowing an admin in to fix things until the security posture is restored.
And the last principle here really gets at design philosophy itself. Economy of mechanism.
This one is a plea for simplicity. Complexity is the enemy of security. The economy of mechanism principle states that your protection mechanisms, the actual code that enforces security, should be as simple and small as possible.
Why is that so important?
Because you need to be able to understand it, to audit it, to be certain there are no hidden backdoors or unintended access paths. The more complex your security code is, the more places there are for bugs and attackers to hide.
Okay, so once an organization buys into these principles, they need to measure their progress. This leads us to the big security maturity models. And for you studying this, knowing the difference between the two is key. Let's start with BSIM.
BSIM, that's the Building Security and Maturity Model. Like we said before, the key word here is descriptive. BSIM does not tell you what you should do.
It tells you what other successful organizations actually do.
Precisely. It's a massive, data-driven study of real-world software security initiatives. It's for benchmarking. You use it to see how your security practices stack up against your peers in the industry.
It's a reality check.
It's a reality check that's incredibly useful for getting executive buy-in. You can present data that says, hey, companies of our size in our industry are performing these 12 security activities, and we're only doing 4 of them.
And it breaks those activities down into 4 big domains, right?
Yep. Governance, which is how the program is run. Intelligence, which is about collecting security knowledge. SSTL touch points, the hands-on stuff like code review. And deployment, which covers security and production.
That sets up a perfect contrast with the other major model, OpenSAM.
Right. If BSIM is descriptive, OpenSAM, the software assurance maturity model, is prescriptive.
It's the roadmap.
It is the roadmap. BSIM tells you where you are. OpenSAM tells you how to get where you need to go. It provides a flexible framework for analyzing your posture and then improving it step by step.
Yeah.
across different maturity levels, usually from 0 to 3.
So you could use them together.
Yeah.
Use BSIM to find a weakness.
And then use OpenSAM to build a plan to fix it.
Oh, exactly.
Let's say BSIM shows you're weak on threat modeling. You turn to OpenSAM, and it would give you a concrete set of activities to implement to get from, say, level 1 maturity to level 2 in that specific practice.
It makes improvement measurable.
Which is essential.
Beyond these big models, security architects lean on a whole ecosystem of external standards and resources. What are the must-knows?
You have to speak the language of the industry. So first, there's NIST, the National Institute of Standards and Technology. They provide tons of foundational guidance on secure SDLCs.
And then there are the resources that track what attackers are actually doing right now.
Right, the living documents. You've got the SANS Top 25 and the OWASP Top 10. These lists rank the most common and most dangerous real-world software weaknesses. If you're trying to prioritize your training or your code reviews, these tell you where to focus for the biggest impact.
And when a specific vulnerability is found, we need a common name for it.
That's the job of CVE, Common Vulnerabilities and Exposures. It provides a unique ID number, like CVE 2023 something, for every publicly known vulnerability. This is absolutely critical for interoperability between all the different security tools and teams.
And for more formal, compliance-driven organizations.
They'll often lean on standards like ISO IE 27034, which is a formal framework for embedding security requirements right into your development process.
Now, this whole SDL process isn't just run by developers. It needs specialized roles. Let's define the key players. Who's at the top of the technical food chain?
That would be the software security architect. This is the person who owns the high-level security design. They're choosing the frameworks, defining the secure coding standards, and leading the critical threat modeling sessions. They draw the blueprint for security.
But you can't have security be just a top-down mandate. It has to live within the teams.
And that's the role of the security champion. These are developers or QA engineers who are embedded right in the Scrum teams. They get extra security training, and they act as the first point of contact for security questions.
So they're a bridge.
They're a bridge between the architects and the daily grind of coding. They help make sure security isn't a bottleneck.
And who keeps the trains running on time for all of this?
That's the Scrum Master or Project Manager. Their job is to facilitate the process and make sure those security milestones we're about to talk about are actually met, not just skipped when deadlines get tight.
Okay, let's get into that process. Phase A1. Security assessment. This is the discovery phase where that shift left philosophy gets real.
This is where it starts. A1 is all about defining the objectives, the scope, and the methodology. And the most important rule is that security team involvement here is mandatory. It cannot be optional.
And within A1, there's a critical gate, especially with modern data privacy laws. What's the one assessment that absolutely has to start here?
The Privacy Impact Assessment, or PIA. If your product is going to touch any kind of sensitive data, PII, PCI data for credit cards, health information, you name it, the PIA process must kick off in A1. You cannot wait.
That seems like a huge undertaking. With laws like GDPR and CCPA, what actually goes into that PIA plan?
It's the blueprint for privacy by design. The plan has to include a summary of all the relevant legislation, the specific process steps you'll follow for handling data, the technologies you'll use like encryption or anonymization, and any other resources you'll need for compliance.
A1 is also where you establish the initial risk profile. How do you figure out how much security is enough?
You look at it from three angles. First, the technical environment. Is this a simple web app or a complex multi-cloud system? Second, the regulatory and geographic constraints. Where will your users be? And third, and this is crucial, the target adversary.
You mean, who are you expecting to attack you?
Exactly. Are you defending against casual script kiddies? Or are you building a system that needs to withstand a persistent, well-funded nation-state attacker? The answer dramatically changes your security budget and priorities.
So at the end of A1, what are the concrete things you walk away with?
You have three key deliverables. The SDL project outline, which bakes all these security gates into the main project schedule. You have the initial third-party software list, which is the start of your supply chain audit. And you have that initial threat profile, which serves as the direct input for the next very intense phase.
Which is phase A2, architecture, the analytical heart of the SDL, where we get into threat modeling.
Right. And we have to be clear, threat modeling is not just a bunch of people in a room brainstorming scary ideas. It is a structured, systematic process, usually run by the security architect or a very experienced champion.
It's about thinking like an adversary.
Systematically thinking like an adversary. And to do that, you need a map of the system.
The data flow diagram, or DFD.
The DFD is the essential blueprint. It's a visual map of how data moves through your system. It has a few key components. You've got external entities like users, which are rectangles. You have processes, the circles where logic happens. Data stores, which look like two parallel lines for your databases or file systems. And data flows, the arrows connecting everything.
But out of all of those, the most important element on the entire diagram is that dashed line, the trust boundary.
The trust boundary is everything. It's the line on the map where the rules change. It separates areas of different privilege levels. The line between the public internet and your internal network, for example, is a critical trust boundary.
And the number one rule of a trust boundary.
Any data that crosses that line from a less trusted zone to a more trusted zone must be treated as hostile. You have to assume it's malicious until you prove otherwise. That's where you put your most stringent checks, like input validation.
Okay, so you have the DFD, you know where your boundaries are. Now you have to systematically find the threats. This is where STRIDE comes in.
STRIDE is the mnemonic that ensures you don't miss a category of threat. It forces you to look at the system from different attack angles, each one mapping back to our core security goals.
Let's run through it. S is for spoofing.
An attack on authentication. Can someone pretend to be a valid user? T is for tampering.
An attack on integrity.
Exactly. R is for repudiation, which violates non-repudiation. Can a user deny they did something? I is for information disclosure.
Confidentiality.
D is for denial of service, an attack on availability. And finally, E is for elevation of privilege, which is an attack on authorization.
So STRIDE helps you find and classify the threats. But you can't fix everything at once. You need to prioritize. That's DRID's job.
Right. DREAD is a risk scoring model. For each threat you found with STRIDE, you score it across 5 categories: damage, reproducibility, exploitability, affected users, and discoverability.
And the total score tells you how urgent it is. A score of, say, 13, 15 is a high priority, drop everything and fix it kind of threat.
Precisely. That ranked list of threats becomes your risk mitigation plan. High-risk threats might require you to go back and change the whole architecture. Medium risks get standard controls. And for some very low-risk items, you might make a documented business decision to just accept the risk.
So the output from A2 is this incredibly detailed blueprint for defense.
It is. You walk out with your DFDs, your STRIDE reports, your DREAD scores, and a formal architectural threat analysis. It's a massive amount of work, but it saves you from disaster later on.
Which brings us to phase A3, design and development. This is where the rubber meets the road, translating all that analysis into actual code. For anyone studying, the section on technical implementation is heavily weighted.
And in A3, the key is clarity. Dev teams need to know exactly what security requirements they need to build. And those requirements usually fall into 2 big categories.
Let's talk about the baseline stuff first. The things you have to do everywhere, all the time.
Those are what we call every sprint requirements. They are the non-negotiable, universal rules of security hygiene. Things like all user input must be validated, all passwords must be hashed securely, all critical actions must require MFA. You do these things on every single feature, no exceptions.
And then there are the requirements that only pop up when you use a specific technology.
We call those bucket requirements. Think of it like this. If your team decides not to use, say, remote procedure calls, or RPC, then you don't need to worry about the RPC security bucket. But the moment they decide to use it,
the bucket opens up and a whole new set of specific requirements and tests like RPC fuzzing suddenly apply.
Exactly. It keeps the requirements relevant and not overwhelming.
Let's get into one of those core practices, handling input.
Input sanitization and validation. This is probably the single most important defensive technique in web applications. You have to work from the assumption that all input from any source is hostile.
So you validate it to make sure it looks like what you expect.
And you sanitize it to strip out any potentially dangerous characters before you ever process it. This is your frontline defense against a huge class of attacks.
And what about when things go wrong in the code? What's the danger with how we handle errors?
Improper error handling is a primary cause of information leakage. This is a huge vulnerability. If your application crashes and spits out a raw stack trace to the user's browser,
you're giving the attacker a roadmap to your internals.
A complete roadmap. They see database names, internal paths, library versions, everything they need to plan a more sophisticated attack. So the rule is log the detailed error internally for your developers, but only ever show the user a generic, unhelpful error message.
Okay, so that's A3. Now in A4, the readiness phase, we have to prove that we actually built it securely. This is all about testing. Let's start with the difference between the automated analysis methods.
The big divide is static versus dynamic analysis, SAST versus DAST.
Let's start with SAST, static analysis.
SAST tools scan your source code directly without ever running the application. They're looking for bad patterns in the code itself, things like hard-coded passwords, use of weak encryption, or queries that look vulnerable to SQL injection.
And you can run this very early, right? Like as the developer's writing the code.
That's its huge advantage. You get immediate feedback. The downside, its blind spot, is the runtime environment. A SaaS tool can't tell you if your server is misconfigured or if your firewall rules are wrong because it never actually runs the code.
And that's exactly where DAST, dynamic analysis, comes in.
DAST tests the application while it's running. It acts like a user or an attacker and sends real requests to the application, then watches how it behaves. It's great at finding those runtime issues that SaaS is blind to, like configuration errors or session management problems.
But its weakness is that it's more of a black box. It can't see the internal logic.
Exactly. So they're complementary. You really need both.
There's also a specialized type of DAST that's all about breaking things, right? Fuzzing.
Fuzz testing, or fuzzing, is a blast. It's basically an automated process that throws millions of pieces of malformed, random, and unexpected data at every input it can find.
The goal isn't to test logic, it's to see if the application crashes.
Precisely. It's a test of robustness. You're looking for buffer overflows, unhandled exceptions, basically any way to make the application fall over under hostile conditions.
We can also categorize testing by the tester's level of knowledge. White box, black box, and gray box.
Right. White box is when the tester has all the keys to the kingdom. Source code, architecture diagrams, everything. This lets them find very deep, complex logic flaws.
Black box is the opposite.
Complete opposite. The tester knows nothing about the internals. They're simulating a real external attacker. And gray box is the middle ground. Maybe they have a standard user account so they can test what a malicious insider might be able to do.
With all these amazing tools, why is manual code review still so critical?
Because automated tools are very good at finding known, simple patterns. They are terrible at understanding business logic. They can't tell you if your complex authorization model has a flaw that lets a manager approve their own expense report. Only an experienced human can understand that context.
And because that human time is so expensive, what's the very first step you have to take?
You must, first and foremost, define the objectives of the security code review. You have to focus that precious expert time on the absolute highest risk parts of the application that you identified back in threat modeling.
Okay, let's use that technical knowledge and apply it to some of the most common attacks you'll be tested on. Let's start with the king, SQL injection.
Slowly. The vulnerability here is a failure to separate code from data. It happens when you take user input and just stitch it directly into a database query string. An attacker can then put database commands into their input.
Like OR11.
And completely change the logic of your query, letting them dump or destroy your entire database.
So what is the one definitive countermeasure for SQL?
There's only one right answer. Parameterized queries, sometimes called prepared statements. This technique sends the command structure to the database first, and then sends the user data separately as parameters. The database engine never, ever executes the user data. It just treats it as a value.
It physically separates the code from the data.
And that completely neutralizes the attack.
Okay, next up. Cross-site scripting, or XSS. This one is different because it targets the user's browser.
Exactly. With XSS, the attacker injects a malicious script, usually JavaScript, into the content of a website. When another victim views that page, the script runs in their browser in the context of their session.
And it can do things like steal their session cookies or perform actions on their behalf.
All without them knowing. It's an attack on their integrity and confidentiality.
What's the required defense here? How do you defang that malicious script?
The core mitigation is output encoding. Before you display any user-supplied content back in the browser, you have to encode any special characters. So the less than sign becomes NLP.
So the browser just displays it as text instead of interpreting it as the start of a script tag.
Exactly. The payload is rendered harmless.
Let's touch on a classic, especially in older languages. The buffer overflow.
Ah, yes, the buffer overflow. This is deeply tied to languages that force you to manage memory manually, like C and C++. It's when you try to write more data into a memory buffer than it was designed to hold, and you end up overwriting adjacent memory.
which an attacker can use to inject their own code and have it executed.
A classic and very powerful attack that could lead to a full system compromise.
We also see a whole category called broken authentication. What does that cover?
It's a broad one. It covers everything from weak password policies and improper password hashing to bad session management. It's about fundamental failures in how you verify who a user is.
Let's get specific. How do you defend against a brute force attack where someone is just trying to guess passwords over and over?
It has to be a layered defense. First, you need a strong password policy as a security requirement. Minimum length, complexity with uppercase, numbers, special characters. But you also need system controls, like account lockouts after a few failed attempts and maybe a CAP ETCHA to stop the automated bots.
And what about the human element, the social engineering attacks? How do we formally define a phishing attack?
Phishing is a very specific type of social engineering. It's all about tricking users into providing sensitive information. They create fake emails or websites that look legitimate to fool people into handing over their credentials or credit card numbers.
Let's pivot to insider threats. If you're trying to protect your data from your own employees, what's the highest priority action?
It goes right back to the principle of least privilege. The number one priority is to implement strict data access controls and monitoring. Make sure people can only access the data they absolutely need for their job, and then log and audit everything they do with it.
Perfect. Lastly, let's clarify two common network controls. What is the specific job of a web application firewall, a WAFF?
A WAF is in front of your web application, and its specific job is to filter and monitor HTTP traffic. It can inspect the requests and responses and block common known ACAC patterns like a classic SQL string before it even gets to your code.
And an access control list, or ACL?
An ACL is a more general purpose tool. Its function is to define permissions for users or groups on a resource. It's the list that says this user is allowed to access this file or this IP address is allowed to connect to this server.
Okay, we've built the app, we've tested it, now we're at phase A5, the ship phase, the final gate before release. This is all about process and workflow. What has to happen here?
A5 is the final comprehensive check. It includes the final security review, a final privacy review, one last round of vulnerability scanning, and, most importantly, penetration testing.
You also mentioned the open source licensing review. Why is that so critical right at the end?
Because modern software isn't built, it's assembled from thousands of open source components. You have to meticulously check the licenses of every single one to avoid huge legal risks. And you have to check them for known vulnerabilities because you inherit their security debt. It's a massive supply chain problem.
And this is all wrapped up in the A5 policy compliance analysis.
That's the final sign-off. It's the documented proof that the product has met every security and privacy mandate that was established all the way back in A1 and A2.
Tell me more about the penetration testing in this phase. How is it different from the DAST we did in A4?
The pen test in A5 is about exploitation, not just discovery. It's usually done by an independent third party to get a fresh, unbiased perspective. They don't just find a flaw, they try to actually exploit it to see how much damage they can do, simulating a real hacker.
And once that final review is done, what are the possible outcomes?
There are three. The best is passed, everything is good to go. The next is passed with exceptions. This means there are some minor, low-risk issues left, but you have a documented plan to fix them in the very next patch, and the business accepts the temporary risk.
And the bad one.
Not past escalation required. This means a high-severity, unacceptable risk was found. The release is blocked, and the decision goes up to senior leadership. They either delay the launch to fix it, or they have to formally sign off on accepting a potentially catastrophic risk.
So the product finally ships, but it's not over. We enter post-release support, or PRSA. This is all about sustainment.
Right. Security is a continuous process. A key rule here is that any change to the live system, a new feature, an architectural tweak, has to re-trigger the SDL. And this whole phase is managed by a specialized team, the Product Security Incident Response Team, or PSIRT.
The PSIRT's job is to handle vulnerabilities discovered in the wild. They have a very specific high-stakes process. Once they've confirmed a bug is real and they've developed and tested a patch, what is the very next critical step?
This sequence is vital. After the fix is built and tested, the very next step is to notify customers that the fix is available. You absolutely cannot disclose the details of the vulnerability to the public before the patch is available. That would be painting a giant target on your customers' backs.
PRSA also has to deal with long-term problems like old code and company acquisitions.
Definitely. You need a strategy for managing legacy code, balancing the cost of fixing old security debt versus the risk it carries. And for mergers and acquisitions, you have to perform intense security due diligence on any company you buy so you don't unknowingly inherit all of their hidden security problems.
So the deliverables in this phase are all about readiness and documentation.
Exactly. A documented vulnerability disclosure process, reports from ongoing third-party audits, and a clear strategy for managing that legacy code risk over time.
And there we have it, a full cradle-to-grave journey through secure software design, hitting the definitions, the process, and the technical controls right from your source material.
And the structure is so important to remember. A1 is discovery and PIA. A2 is threat modeling with DFDs and StrideTread. A3 and A4 are about building and testing with SAST and DAST. A5 is that final gate with pen testing. And PRSA is all about long-term sustainment with the PSRT.
And don't forget those core ideas. The economic power of the shift-left argument, the difference between descriptive BSIM for benchmarking and prescriptive OpenSAM for your roadmap.
And please commit those countermeasures to memory. Parameterize queries for SQL injection, output encoding for cross-site scripting, and the principle of least privilege as the guiding rule for everything related to access control.
So to wrap this all up, here's a final thought for you to chew on, one that connects a few of these big strategic choices. We've established that expert human time for manual code review is your most precious, limited, and expensive resource.
And we also know that certain languages, like C and C++, are just inherently riskier from a memory safety perspective. They are far more prone to things like buffer overflows than a memory-safe language.
So here's the decision you have to make as the security architect. With your finite budget for manual review, where do you get the biggest return on investment? Should you focus all that precious expert time on the code written in the riskiest languages like C++, OLF, to stamp out those specific memory flaws?
Or is the smarter move to dedicate that human expertise to reviewing the most sensitive architectural components, the critical trust boundaries, and high-risk business logic you identified way back in your A2 threat model, regardless of what language they were written in? It's a fascinating tension.
Yeah.
Do you focus on minimizing specific language risk or on maximizing overall system resilience?